Good morning. Suppose that a flock of 20 pigeons flies into a set of 19 pigeonholes to roost. Because there are 20 pigeons but only 19 pigeonholes, at least one of these 19 pigeonholes must have at least 2 pigeons in it. To see why this is true, note that if each pigeonhole had at most 1 pigeon in it, at most 19 pigeons, 1 per hole, could be accommodated. This illustrates the general principle called the pigeonhole principle, which states that if there are more pigeons than pigeonholes, then there must be at least 1 pigeonhole with at least 2 pigeons in it. Of course, this principle applies to other objects besides pigeons and pigeonholes. Theorem 1, the pigeonhole principle. If k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least 1 box containing 2 or more of the objects. Corollary 1. A function f from a set with k plus 1 or more elements to a set of k elements is not one-to-one. Example 1. Among any group of 367 people, there must be at least 2 with the same birthday because there are only 366 possible birthdays. Example 2. In any group of 27 English words, there must be at least 2 with the same first letter because there are 26 letters in the English alphabet. Example 3. How many students must be in a class to guarantee that at least 2 students receive the same score on the final exam if the exam is graded on a scale from 0 to 100 points? There are 101 possible scores on the final. The pigeonhole principle shows that among any 102 students, there must be at least 2 students with the same score. The generalized pigeonhole principle. Theorem 2. If n objects are placed into k boxes, there must be at least 1 box containing the ceiling of n divided by k objects. Example 5, among 100 people, there must be at least the ceiling divided by 100 divided by 12 equal 9 who were born in the same month. Example 6, what is the minimum number of students required in a discrete mathematics class to be sure that at least 6 will receive the same grade if there are 5 possible grades, A, B, C, D, and F? Solution. The minimum number of students needed to ensure that at least 6 students receive the same grade is the smallest integer n such that the ceiling of n divided by 5 is equal to 6. The smallest such integer is n equal 5 times 5 plus 1 is 26. If you have only 25 students, it is possible for there to be 5 who have received each grade so that no 6 students have received the same grade. Thus, 26 is the minimum number of students needed to ensure that at least 6 students will receive the same grade. Example 7.1. How many cards must be selected from a standard deck of 52 cards to guarantee that at least 3 cards of the same suit are chosen? Solution. Suppose there are 4 boxes, 1 for each suit, and as cards are selected, they are placed in a box reserved for the cards of that suit. Using the generalized pigeonhole principle, we see that if n cards are selected, there is at least 1 box containing the ceiling of n divided by 4 cards. Consequently, we know that at least 3 cards of one suit are selected if n divided by 4 is greater than or equal to 3. The smallest integer n such that the ceiling of n divided by 4 is greater than or equal to 3 is 2 times 4 plus 1 is equal to 9. So 9 cards suffice. Note that if 8 cards are selected, it is possible to have 2 cards of each suit, so no more than 8 cards are needed. Consequently, 9 cards must be selected to guarantee that at least 3 cards of one suit are chosen. One good way to think about this is to note that after the 8th card is chosen, there is no way to avoid having the 3rd card of some suit. Example 7.2. How many cards must be selected to guarantee that at least 3 hearts are selected? Solution. We do not use the generalized pigeonhole principle to answer this question because we want to make sure that there are 3 hearts, not just 3 cards of one suit. Note that in the worst case, we can select all the clubs, all the diamonds, and all the spades, 39 cards in all, before we select a single heart. The next 3 cards will be all hearts, so we may need to select, in the worst possible case, 42 cards to get 3 hearts. Example 8. What is the least number of area codes needed to guarantee that the 25 million phones in a state can be assigned distinct 10-digit telephone numbers? Assume the telephone numbers are the form NXX hyphen NXX hyphen quadruple X, where the first 3 digits form the area code. N represents a digit from 2 to 9, and X represents any digit. Solution. There are 8 million different phone numbers of the form NXX quadruple X, as shown in example 8 of section 6.1. Hence, by the generalized pigeonhole principle, among 25 million telephones, at least the ceiling of 25 million divided by 8 million of them will have identical phone numbers. Hence, at least 4 area codes are required to ensure that all 10-digit numbers are different. Some elegant applications of the pigeonhole principle. Example 10. During a month with 30 days, a baseball team plays at least 1 game a day, but no more than 45 games. Show that there must be a period of some number of consecutive days during which the team must play exactly 14 games. Solution. Let AJ be the number of games played on or before the j day of the month. Then let A1, A2 on up to A30 be an increasing sequence of distinct positive integers with 1 less than or equal to A sub j less than or equal to 45. Moreover, A1 plus 14, A2 plus 14, all the way down to A30 14 is also an increasing sequence of positive integers with 15 less than or equal to A sub j plus 14 less than or equal to 59. The 60 positive integers, A1 through A30, A1 plus 14, A2 plus 14, all the way down to A30 plus 14, are all less than or equal to 59. Hence, by the pigeonhole principle, 2 of these integers are equal. Because the integers j equal 1 to 30, are all distinct, and the integers aj plus 14, j equal 1 to 30 are all distinct, there must be indices I and j with a sub I equal a sub j plus 14. This means exactly 14 games were played from day j sub 1 to day I. Example 11. Show that among any n plus 1 positive integers not exceeding 2n, there must be an integer that divides one of the other integers. Solution. We write each of the n plus 1 integers a1 through an plus 1 as a power of 2 times an odd integer. In other words, we let a sub j equal 2 to the k, q sub j, for j equal 1 to n plus 1, where k sub j is a non-negative integer and q sub j is odd. Theorem 3. Every sequence of n plus 1 distinct real numbers contains a subsequence of length n plus 1 that is either strictly increasing or strictly decreasing. Example 12. The sequence 8, 11, 9, 1, 4, 6, 12, 10, 5, 7 contains 10 items. Note that 10 is equal to 3 squared plus 1. There are 4 increasing subsequences of length 4, namely 1, 4, 6, 12, 1, 4, 6, 7, 1, 4, 6, 10, and 1, 4, 5, 7. There is also a decreasing subsequence of length 4, namely 11, 9, 6, 5. Example 13. Assume that in a group of 6 people, each pair of individuals consists of 2 friends or 2 enemies. Show that there are either 3 mutual friends or 3 mutual enemies in the group. Solution. Let A be one of the 6 people. Of the 5 other people in the group, there are either 3 or more who are friends of A, or 3 or more who are enemies of A. This follows from the generalized pigeonhole principle because when 5 objects are divided into 2 sets, one of the set has at least 5, the ceiling of 5 divided by 2 equal 3 elements. In the former case, suppose that B, C, and D are friends of A. If any 2 of these 3 individuals are friends, then these 2 and A form a group of 3 mutual friends. Otherwise, B, C, and D form a set of 3 mutual enemies. The proof in the latter case, when there are 3 or more energies, proceeds in a similar manner. Here are some sample exercises. Show that in any set of 6 classes, each meeting regularly once a week on a particular day of the week, that there must be 2 that meet on the same day, no matter, assuming that no classes are held on the weekends. Solution: there are 6 classes. These are the pigeons. There are 5 days in which classes may meet, Monday through Friday. These are the pigeonholes. Each class must meet on a day. Each pigeon must occupy a pigeonhole. By the pigeonhole principle, at least one day must contain at least 2 classes. 3. A drawer contains a dozen brown socks and a dozen black socks, all unmatched. A man takes socks out at random in the dark. How many socks must he take out to be sure that it is at least 2 socks of the same color? Solution: there are 2 colors. These are the pigeonholes. We want to know the least number of pigeons needed to ensure that at least one of the pigeonholes contains 2 pigeons. By the pigeonhole principle, the answer is 3. If 3 socks are taken from the drawer, at least 2 of them must be the same color. On the other hand, if 2 socks are not enough, 2 socks are not enough because one might be brown and the other black. Note that the number of socks was irrelevant, assuming it was at least 3. How many socks must he take out to be sure he has at least 2 black socks? He needs to take out 14 socks in order to ensure that he has at least 2 black socks. If he does not do so, then in most 12 of them are brown, so that at least 2 are black. On the other hand, if he removes 13 or fewer socks, then it is possible for 12 of them to be brown, and he might not get his pair of black socks. This time, the number of socks did matter. How many ordered pairs of integers a, b are needed to guarantee that there are 2 ordered pairs a subscript 1, b subscript 1, and a subscript 2, b subscript 2, such that a1 mod 3 equal a2 mod 3 and b1 mod 3 equal b2 mod 3? Working modulo 3, there are 9 pairs, 0, 0, 0, 1, all the way up to 2, 2. Thus, we could have 9 ordered pairs of integers a, b, such that no 2 of them were equal when reduced modulo 3. The pigeonhole principle guarantees that if we have 10 such pairs, then at least 2 of them will have the same coordinates modulo 3.